All right, so welcome back. We are still in section 1.3, and we're just going to go ahead and finish it up. At this point in time, I'm going to use language like linear combination, span, etc., and I'm not going to continue to revisit what this language, these terms mean. I would suggest, I appreciate your ability to just suffer through and continue to watch videos. But if you still feel like the language I'm using is confusing you, please, you do whatever you would like to do. But I can only tell you, I've been teaching this for many, many years. If you let the vocabulary build up, if you let your misunderstanding of the vocabulary, if you let it build up too large, it becomes really hard to catch up. So please, if you have to go back and revisit those lectures, if you have to seek the textbook, if you have to seek some other videos online to try to help you understand the concepts and the vocabulary, please do. Please, please, please do. Okay, so example 5 is an amazing example. Very, very, very important example. Probably the most important out of this entire section. Okay, so it says let a sub 1, a sub 2, and b be defined as follows, right? Let's try to make sure we understand. So we got 3 rows, 1 column, right? So this is a 3 by 1. This is a 3 by 1. This is a 3 by 1. This meets our definition of these are all column vectors. Okay, so we are given 3 vectors. Given those 3 vectors, what would they like us to do? It says determine whether vector B can be generated, right, written, as a linear combination of vectors a sub 1 and a sub 2. Quite simply, is there a way, is vector B in the span of vector a sub 1 and a sub 2? Can you travel along the a sub 1 line and then travel along the a sub 2 line and ever arrive at B? Now, I've been using language like scalars, but in linear algebra, well, it does float back and forth. It depends on if you're talking, but I won't go into the weeds here. But for now, scalar and weights are the same thing. So notice how that is determine whether the weights x sub 1 and x sub 2 exist such that. Now the only difference is, see, we had a c sub 1 and a c sub 2 here, right? We had a c sub 1 here, we had a c sub 2 here. They are using x sub 1 and x sub 2. That's not a problem. But instead of calling them scalars, they're calling them weights. And the terminology, you'll see why they choose this language very soon. But what is it that they want? They determine whether given some weights, x sub 1 and x sub 2, is it possible for you to reach vector B? So do these weights exist such that this equation has a solution? And if it is, find it. If it does have a solution, find it. In other words, find what x sub 1 and x sub 2 must be if it exists. Okay, so what I'm going to do is I'm going to go ahead and I'm going to go ahead and write x sub 1 times a sub 1 plus x sub 2 times a sub 2 is equal to b. And what I'm going to do right now is I'm going to go ahead and insert the vectors in this equation. So now the equation is x sub 1 multiplied by 1, negative 2, negative 5 plus x sub 2 multiplied by 2, 5, 6. And that must equal vector b, which is 7, 4, negative 3. And let me just make sure I haven't made any silly mistakes. So 1, negative 2, negative 5, 2, 5, 6, 7, 4, negative 3. Okay. So here it is. So the game is it possible for you to find some weight, x sub 1, x sub 2, some scalar, x sub 1, x sub 2, such that when you distribute that number to this vector, and then you distribute that number to this vector, once you combine them, you get vector b. All right. Well, if you like, you can spend hours playing with different numbers, right? Even if you're fairly savvy doing math in your head, it's still going to take you a while to figure out what those numbers are, if they even exist. So there must be a better way, and there is a better way. Let me see if I can try to explain how you would do it. So what we're going to do is, let's go ahead and distribute this x sub 1 and this x sub 2. Right? We're going to distribute x sub 1 inside here, inside this vector, just like you would scale anything. Ready? So now it looks like this. So x sub 1 times 1 is just x sub 1. X sub 1 times negative 2 is negative 2. X sub 2, negative 5. Oh, I'm so sorry. I got to be careful. So x sub 1 times negative 2 is negative 2 x sub 1. X sub 1 times negative 5 is negative 5 x sub 1. Plus, okay, ready? Now let's distribute the x sub 2. So x sub 2 times 2, x sub 2 times 5, x sub 2 times 6. So I have 2, x sub 2, 5, x sub 2, 6, x sub 2. And again, we know what it is equal to. 7, 4, negative 3. Okay. So at this stage, we are going to call upon the tool of matrices to help us. So I'm going to take this information, just to let you know where we're going with this. I'm going to take this information, is all going to be placed into a matrix. And then you probably have guessed it, we're going to RREF that matrix and let the calculator do the solving for us, right? Let the calculator run that algorithm. Not that you and I can't use those row operations, right? It's just, hey, the technology is there to save us time so we can focus on other things. So let's go ahead and I'm gonna be placing this information here. For some of you, if this looks gimmicky, like how do you go from what we have now into a matrix? Well, if you'd like, you can think of it as a system. You can think of the system as x sub 1 plus 2x sub 2 equals 7. And now you should be able to see how we would go from a system into a matrix. So if you need that extra step to get here, by all means do it. In fact, I'm actually just going to go ahead and write this in system form. This is an optional step, right? You don't have to do this, say, for your tests. It's just easier to visualize how do we get to the matrix if I place it back into a system first. And negative 5x sub 1 plus 6x sub 2 is equal to negative 3. Now, if you had been able to follow my previous lectures, you should easily be able to get from a system to a matrix. But isn't it quite interesting how we are just adding up vectors and then somehow the sum of vectors can be thought of as a system. And then isn't it interesting how the system can be thought of as a matrix? And now you're starting to see the interconnectedness of all of this. So let's go ahead and write the matrix. So this would be 1, -2, -5. Then we got 2, 5, 6. And then since it's augmented matrix, the solution region would be 7, 4, -3. Okay, now at this point, I have to, you'll have to either pause the video and you can RREF this matrix if you like. That's right, so that's a 3 by 3 matrix. But I'm going to go ahead and do that. So this is what I get. Right? So when I RREF, when I reduce row echelon form this matrix, this is the row reduced form of that matrix. So now your answer is right in front of you. Remember that the equations represent the rows. So equation 1, row 1. Equation 2, row 2. But the columns represent the variables. So anything in column 1 is dealing with x sub 1. Anything in column 2 is dealing with x sub 2. Right? Now, with that in mind, let's make sense of this. So we translate this to mean x sub 1 is equal to 3, x sub 2 is equal to 2. What have you just done? What you've just done is you figured out what the weights are, such that if I scale this vector by 3 and I scale this vector by 2, once I scale and add, I am able to reach this other vector, b. Absolutely amazing. It's absolutely amazing that the scalars of your vectors, the weights of your vectors, can be translated to the variables of your systems and your matrix. And the solution to the matrix is the solution of the scalars of your vector equation. Absolutely amazing. The solution to systems are weights of vectors. I'll say that again. The solution to systems are the weights of vectors. All right, so hopefully on your end this is not as glossy or distorted in its image as it is, at least in my eyes. But we call this form, right? I'm going to go back because I need to make sure you understand it. We call this form here the vector equation. And what we figured out is that the vector equation has the same solution as the linear system whose augmented matrix is given, right? Same solution. Now, so in that previous example, vector B can be generated as a linear combination. Vector B is in the span of vectors a sub 1 and a sub 2. All right. So this is more or less, I've already given you the information here. yeah, I mean, you can pause and kind of read through the language here, but I've given you all the information of that definition. I haven't been as formal as this definition. It's more or less been in other words, but all the important information has been given to you. All right. So this information also has been given to you. So the span of vector v, they're just trying to give you an idea of the span of various vectors. So this little image right here is kind of important. Let me see if I can try to explain this. So assume vector u and assume vector v. Now you know that with two vectors, you can reach all the points in a plane, right? If you were to discuss the span of u and v, well, it is a plane. Now, depending on if u and v are in the dimension that you're in, but let's say u is in 3 dimensions, v is in 3 dimensions. This might be easier in an example, but nevertheless, as long as you can imagine a plane in space, right? Can you imagine like for just an analogy, like if you have a piece of paper, right? It can represent, if you hold up a piece of paper, that is a plane in 3-dimensional space, if you will. I understand that it's not actually, but I promise you I do understand that. But just to serve as a visual. Okay. So listen, you should work through example 6 on your own. I will go ahead and tell you that this vector b is not in the span of these two vectors. In other words, you cannot reach this vector b, given linear combinations of this. You would do example 6 the exact same way we did example 5. You should try it just to make sure that you can do it. But you should arrive at a scenario where it's impossible to reach vector b. And remember, if you ever are left with a situation like this, where notice that you have a statement 0 is equal to 1, right? So you have a built-in contradiction. That is a way of saying that the matrix is inconsistent, which is a way of saying that you cannot arrive, b is not in the span. All right, so what I will do is very last example for this section is let's if you're like me, all of this theory is great, but I do want to see some type of word problem, some type of utility, so that I can understand what it is. What am I learning this stuff for? So let's take a look at this is actually pretty awesome. Something I told you, many of you know, I own a business, I own a recycling company, and I've used tools like this before, okay, in my own business. But anyway, let me see if I can start off here. So we'll come back to this little equation. Let me read. So it says a company manufactures 2 products, right? So if you're a company, you make 2 products. I don't know. Peanut butter and calculators. I don't know why you have specialized in those 2, but those are your 2 products for this analogy. Now, it says for $1 worth of product B, the company spends 45 cents on material, 25 cents on labor, and 15 cents on overhead. Let's see if you can make sense. So here's I'm going to rewrite this guy. So remember, vector B is some product that you make. Now, it cost money to make this product. Now, for product B, it cost 45 cents. What was that for material? It cost 25 cents for, what was it, labor. And it cost 15 cents for overhead. And in case you don't know what that means, the overhead would be like if you, like at my business, I lease a warehouse in Winchester, and so that's overhead. I have to pay my lease payment every month. It doesn't matter if I sell anything or not. Okay, that is my overhead. So what this is saying is, look, for every $1 worth of product B that you sell, okay, so for every dollar you make from this product, this much of that dollar is going to material, this much is going to labor, this much is going to overhead. Let's keep going. Now, for every dollar worth of product C, so C is your other product, the company spends 40 cents on material, 30 cents on labor, and 15 cents on overhead. So let's go ahead and write out product C. So for product C, it's not as expensive on material. It's only 40 cents on material. A little bit more on labor, 30 cents on labor. And of course, for here, the overhead is the same, right? So your lease payment's the same whether you make product B or product C. Doesn't matter. Okay. So now let's see what we have. So at this stage, we have written the vectors that represent so B and C in this case represent the cost per dollar of income for both products. Right? So if you make $1, it's not like you get to keep all $1, right? There is a cost to make that dollar. 45 cents of that dollar was spent on material, 25 on labor, 25 cents on labor, 15 cents overhead. So there was a cost. This vector is the cost per dollar of income. Now, the first question is, what economic interpretation can be given to the vector 100b? So part A. So the vector 100b. Well, I think you can imagine that thinking about inserting vector B here, it's going to give you the cost of producing $100 worth of product B. All right, so the answer, and I'll write it. So let's go ahead and write 100B is 100 multiplied by 0.45, 0.25, 0.15. Notice that in this case, the scalar is how much money you made from product B, so $100. Once you multiply this tells you the cost. What's the real cost of producing $100 worth of product B? So let me write it. So what the economic interpretation is tells us the cost of producing $100 worth of product B. Okay. So we weren't asked, but if you wanted to know what the costs were of producing $100 worth of product B, well, if you just times everything in here by 100, so 40.45 times 100 is $45, $25, $15. Now, this should all make sense. that if you make $100 from product B, 45 of that 100 is going to material, 25 of that 100 is going to labor, etc. 15 is going to overhead. Okay, so part B, it says, suppose the company wishes to manufacture X sub $1 worth of product B and X sub $2 worth of product C. Let's write that. So X sub 1 worth of product B and X sub $2 worth of product C. Does that make sense? Right? We don't know what that is yet. It says we're asked to give a vector that describes the various costs the company will have for materials, labor, and overhead. And you have to forgive me, my dog has seen a squirrel, I'm sure, outside. Max, it's okay. It's just a squirrel. They're friends. They're friendly. Okay. So in this scenario, it's so funny. In this scenario, let's go ahead and let me make sure that we understand the question. So give a vector that describes the various costs the company will have for materials, labor, and overhead. And I actually have done that right here. So we can give this, let's say that once you choose an X sub 1 and an X sub 2, once you plug, now you can imagine plug B in here, plug C in here. So let me do that because that is actually how you should write your answer. But this is the vector that would describe your total cost of producing these two goods, right? So what was it, 0.40, 0.30, 0.15. That's kind of an easy question, right? I mean, you can call the result of this, I don't care, you can call this W, right? Or C, or what, it doesn't matter. But all I'm trying to say is now that you're sitting down thinking, well, should I make 100? What if I make 100? If I sell 100 worth of product C and I sell 1,000 worth of B, what's my cost going to be? Well, no problem. Plug 1,000 in here, plug 100 in here, do a little bit of arithmetic here, and whatever you get is going to be the per dollar of income cost of producing that much. Does that make sense? So it's really interesting when you think about this. You can kind of play around. If you were a business that did have two products, you truly could play around with these different weights, because what you might find is, hey, there is a happy maximum that I can reach through some combination of these two, right? Now, that is going to conclude 1.3. And again, if you have any questions, don't hesitate to reach out to me. But keep up with the homework, keep up with the vocabulary, and I'll see you in the next video.